Today's topic is brief introduction about the structural analysis. What we are seeing here is the few example of different type of structures. This is a natural structure, and here is the a railway bridge, and this is small house. So what we are seeing here is a suspension bridge model. Here it is subjected to a traffic load shown like this, and because of this traffic load, this deck will go under some deflection, and this pylon may go either right or left, so that we can call it as a rotation about this point. And due to this loading, this cable experience some tension, and these strings experience some tension, and this pylon going to get some compression, and this girder going to get some bending, shear, and if suppose the loading is unsymmetrical, this may also experience some torsion. Same way, all this load, this each and every element will experience corresponding stresses like axial stress, shear stress, bending, torsion. Also, this support going to experience some reaction in vertical direction and horizontal direction, as well as some moment. So since this traffic load is a dynamic load, so when it start moving from left to right or right to left, because of this structure will have some natural frequency. So based on this dynamic load, this structure will go some vibration. So due to this vibration, so it will have experience some velocity acceleration also. Sometimes we have to check the stability of the structure as well as for this both longitudinal direction, transverse direction as well. So basically, the effect of these loads on the physical structure and their component is called a structural analysis. So based on these loading conditions, based on the its excitations, we can classify this loading as two different types. Like suppose the magnitude, direction, and location of the loading is varies very slowly. In case of a temperature, it will vary very slowly, or in case of sulfate means mostly it will be constant. So that load we can call it as a static load. Same, suppose the load is varies very quickly with respect to time, then we can call it as a dynamic load. These are example for that dynamic load: wind load, wave, traffic load, earthquake, and blast. And for some example, there are so many other loadings in both the category. These all are just for the example. Here, what we are seeing here is the seismograph actually. So this is one example for that. Physically, I mean visually, we can see the variation. Like this is the time, and this is the amplitude. So here and all it is constant, and suddenly it is going up and down. So this is one kind of dynamic load. So in this structure, if you see example, sulfate, as we have seen, sulfates are not constant always. It's not changing with respect to time. So this we can call it as a static load. This traffic load maybe comes under the so dynamic load. So basically, structural analysis means to determine the effect of this load on these physical structures and their component, and what could be the response. So to determine this response due to this loading is called structural analysis. Then why required to do this structural analysis, and what are the way to do this, that we will see. There is one way is to do the physical testing. So we have to cast that element, and we have to apply the loading physically, and we have to observe the behavior. Here whatever we are saying, this is a loading frame, and here is some simple RCC beam which is casted, and after attaining certain strength it is fixed in the loading frame. The loads are applied from here. What we are seeing, this is a 2 point loading actually. The one load is coming here, and this is divided into 2 point actually. This is called as a 2 point loading. So here whatever we are seeing, these all are strain gauges. So to measure the deflection, this is comes under structural analysis. So another way of physical test to analyze the foundations or the soil, the supporting soil actually. So here what we are seeing is that this is called as a pile load test actually. Usually pile we will after using the empirical equation we used to design the pile. Pile design means structural design is separate. This is here what could be the dia of the pile and how much length of the pile has to be embedded into the ground. All those things comes under the geotechnical analysis. So after using the empirical equation, usually we will analyze, but before execution, maybe if suppose 100 piles are going to be installed here, at least one or two pile we need to do physical testing like this. Whatever we are seeing, these all are reaction blocks. So the piles, the after casting or maybe driven the pile, so they will do one testing like this, and maybe that in clearly this is under that reaction. What we are seeing is this the reaction. If we see inside here, so this is like a hydraulic jack which is going to apply the load in this direction, and this hydraulic jack going to get the reaction from the whatever we have seen, right, these reaction blocks actually. So suppose if you want to apply estimated load approximately some 5000 kilonewton, this reaction block will be into 2 times 2.5 times based on the factor of safety. So here if you see so many strain gauges are fixed here to measure the settlement of the pile. So finally, so to do this physical test, so we will come to know that what could be the record pile length, and to determine the load settlement behavior of the pile, also to counter check the results obtained from geotechnical engineer from the file driven formula. This is one way of analyzing the doing the physical test. So the another way is to do a mathematical modeling. So nowadays we have the powerful computers and we can do almost whatever we are doing in the physical test, almost exact modeling we can do it in the software, and we can do the analysis. We can match almost close enough the real structural behavior. So to do that, structural analysis will use these all are the branch of science actually: applied mechanics, material science, and the applied mathematics. With the help of these we can arrive this response of the loading. So to do that, to do the mathematical modeling, we should uh, keep something in our mind, like to perform the structural analysis. A structural engineer must determine the information such like what could be the loading and what is the geometry of this structure, and what could be the support conditions here, and what could be the material properties of this particular structure. Say example, here we are seeing one natural structure, coconut tree. So this is the equivalent mathematical model to do the analysis. Since this is a determinate structure, to do this analysis, the equilibrium condition alone sufficient. We may not require the compatibility conditions and all. So this height of this column should be equal to the height of the tree, and these are node 1 and 2. Node 2 is free, and node 1 is idealized as a fixed with spring constant, like in vertical direction, horizontal direction, and rotational. And this may subjected to some wind load, so we have to calculate that load and we have to apply it at node 2 level. So with the help of this equilibrium equation, sum of force equals 0 and sum of moment equals 0, so we can get all these internal forces whatever we have seen right here: deformation, internal force, stress, support condition. If dynamic means velocity, acceleration, also the stability, everything we can find out with the help of this mathematical modeling. So in case of indeterminate structure like this, here both ends are fixed, so the equilibrium equation alone not sufficient. So we need constitutive and compatibility condition as well to solve this problem. So here basically computer use mostly there are lot n number of way to solve this problem as well. Moment area method, Conning's method, virtual work method, n number of methods are there, but this is the stiffness matrix method. So what we are seeing, this is the force matrix, this is stiffness matrix, and this is displacement matrix. So to calculate this stiffness matrix, this load matrix is coming from the external loads, and this stiffness matrix is depends upon the we have to engineer, we have to calculate, and based on our structural arrangement. Say example here, this will have some cross section, and this will have some length, and this will have some material property and support condition. Based on this, we have to calculate the stiffness matrix. So this is very important actually in the difference between the our college theoretical knowledge and between the difference between the theoretical knowledge and the when we started working on the real projects in college days. Our problems are very simple. Problem is already fixed. Before solving, the question is ready. What is the span of the beam, and what is the cross section, what loading going to come, what is the material, Young's modulus, all those things are readily given. Directly we're going to analyze it, and we are going to design it. In a real problem, that is our responsibility. We have to idealize the structure. Say example, if you see in this case, what could be the support condition, what is the length of this element, and what is so this equivalent mathematical model should be formed based on good engineering judgment. Otherwise our analysis will go wrong. So that if you see, yes, this is engineer VK Raina. If you see his quotes, it's if you know the meaning, it's a wonderful quote. Like it is more meaningful to have an approximate solution to the exact problem rather than exact solution to the approximate problem. So our problem itself wrong, or we have not idealized the model well based on engineering judgment. Even though if you are doing after decimals, maybe if you are considering 10 digit also you are in analysis and design, that is waste only. Suppose instead of fixed support, if you are considering a pinned support, all our analysis will go wrong, right? So that is very important in our once you started working on live projects. So whatever we are seeing is the brief introduction about analysis. In this analysis itself depends upon the maybe excitation of loading it, whether it is a static or dynamic. So we have to go for static analysis when we should go for dynamic analysis. Also depends upon the loading. If loads are very light or within their linear range, we can go for linear elastic analysis. If load is very high, then we should consider non-linear analysis. In this non-linear analysis itself, there are different type of nonlinear material nonlinearity, geometrical nonlinearity, and in boundary condition nonlinearity. So these are all we will discuss in detail in upcoming lectures.